Okay, in the last class, we made some remarks about the shortcoming of eigenvalue analysis, and we proposed that instead we would look at receptivity analysis of shear layer. We are still confining our attention to viscous instability mechanism, because that is all encompassing. The study would also include the inviscid modes, as you have seen from the Orson-Feld equation. So, what you do in receptivity study is basically you relate cause and effect. That is what we said. That gives you an sort of a leverage to work out, circumvent some of the problems those were identified by early experimentalists like Schubar and Skramstad. They wanted to find out how to work out the best means by which instability waves could be excited, and this was what they had to say, that in trying to work out a method, they found that method using sound, whether it is a pure noise or random noise, were not at all satisfactory, and all they could do is they could vibrate a ribbon inside the shear layer very close to the wall, not exactly at the wall, but very close to the wall, and they could get those Tolman-Schlichting waves, right. Well, we particularly pointed out that if you are looking for two-dimensional instability modes, acoustics is going to be a very poor candidate, because acoustic excitation is inherently three-dimensional. Nonetheless, eigenvalue analysis obscures your vision to give you some idea about the cause itself. You just simply try to say possible effects, right, through indirectly, that if there were disturbances which would have been adequate to excite those, then what would be the effect. That is the kind of thing. And now, we did talk about free stream turbulence, right. How important it is, because the vibrating ribbon experiment of Schubar-Skramstad showed that you could excite the T s wave by vibrating a ribbon inside the shear layer. But suppose the disturbance is outside the shear layer, that is what your free stream turbulence is most of the time, whether you are flying an aircraft or you are doing an experiment in the tunnel. It is what that you are getting in terms of the background disturbances. Now, this result that you see in front of you is somewhat very intriguing and special, which we did a few years ago. What we tried to do is study the flow past a circular cylinder for a Reynolds number of 53. Why 53? Because earlier theoretical studies have revealed that if you keep your Reynolds number about 47 or 48 or so, then you see this vortex that is shed at the back of a cylinder, okay, circular cylinder. Now, this event is traced to the instability of the flow, right. Now, the question is, then for a Reynolds number of 53, we should see a shedding, and that is what one would like to do. At the same time, last class we did critique about characterizing experimental facilities in terms of a single quantity called turbulent intensity, right, like T u, what you define as a kind of a root mean square disturbance, okay, average disturbance in the physical plane itself. That kind of characterization falls a little short, and that was what we wanted to highlight through this experiment. So, what we did, we fixed the Reynolds number, and we took two cylinders, one of diameter 5 millimeter, another is diameter is 1.8 mm. And to keep that Reynolds number, in this case the tunnel was set at a speed of 17 centimeter per second, and in this case it was much higher. We required 46.9 centimeter per second to simulate the same Reynolds number. Now, forget about all the things that you have been told in the first course in fluid mechanics about similarity parameter. you have been given a steady diet of the idea that if you keep the similarity parameter same, flow would be same. Then we wanted to probe that, and that is what we did. And now you can see, okay, here for this case at a higher velocity, you do see some eddies in the back. Okay. This is a prolonged attached eddy here, which at the tail end of those two eddies gives rise to something like a undulating excitation, something like what we studied in Kelvin-Helmholtz mode, right. That gives rise to breaking up of those attached eddy and gives rise to weak undulation. Now, it is a matter of interpretation. Is this like what we know of the Karman vortex treat in a flow past a cylinder? That is what you see in this other case. For this lower free stream speed, what we notice that very clearly the vortices are shed right from the cylinder itself, right. It is quite unlike this case. Now, why these two flows are too different? That you cannot get from the understanding of that so called TU, because we are working on the same tunnel. So, we have that so called same TU. What you profitably can understand is you try to find out what is the nature of the background disturbance in the tunnel. Well, the same tunnel should have the same background disturbance. Unfortunately, it is not so, because given the different speed, I get different disturbance environment. This is what it looks like for 17 centimeter per second, and this is what it is for 46.9 centimeter per second, the same tunnel. And what is plotted here is the disturbance amplitude versus frequency. And how it is done? We have removed the model. We just simply run the empty tunnel at two different speeds. And can you see the disturbance environment being so different? Now, this is the kind of problem that one does not expect to see. What you notice though, that from the earlier studies, you can find out this Struhal number, the shedding frequency. That is what you may put in a probe little far down, measure the signal, and you will see a characteristic frequency. Time variation, that is what is called as a Struhal number. Now, if you look at the Struhal number, that is a fixed frequency for this particular Reynolds number, and what we did was we just simply zoomed this spectrum around the Struhal number, and in this case you see this is the Struhal number, there is a peak, and this value is something like about 25 to 30 in that range. So, at Struhal number we have the background disturbance, that is the most robust. In contrast, if I look at for this higher speed case, now you see I get the value which is about 10 times smaller. We get 10 times smaller at the Struhal number. So, what happens? This tells you a very clear story that if you do not have the cause, you do not have the adequate effect. So, in this case, cause is strong, 10 times more powerful than this, and that is why you are seeing vortex shedding. So, this is the motivation for doing receptivity, that what you need is the adequate strength of the disturbance field, then only you will see the desired effect, otherwise you will not. Unfortunately, if you would have done instability studies, it will not distinguish, because you are looking at the same Reynolds number, same tunnel, everything same. So, when we did produce this result, I mean this was quite unnerving, especially for people who have just come out from the first course in fluid mechanics, where they have been told time and again this importance of similarity parameters. And here we are saying, well, that is not so, that is not so. What it actually means that there may not be a single similarity parameter that one should be looking at. In this case, of course, the excitation at the relevant frequency, that is frequency spectrum, should also be a independent variable in the study. And if we do not do it, we are going to be baffled like this. So, that is why I would say that please look at our results once again in a different perspective. Okay? We need to really have an intimate knowledge of the input disturbance, and this is what we saw, that in actual flow, even for a flow past a flat plate, Schumacher-Kramstadt did show that natural disturbances are not as sort of coherent as one would like to see in a well designed experiment or in the theory of instability by normal modes. And this we discussed. Now, you can see the so called effect of free stream turbulence for flow past a flat plate. And here you have a complete mishmash. You have different kinds of disturbance environment, and you have different types of transition Reynolds number. And this basically is sufficient for us to be convinced that we need to do a receptivity analysis. And that is what where we actually stopped. We said, what do we do when we perform an instability analysis? What we do is basically we try to solve Orson field equation, and we saw it as a fourth order ordinary differential equation. So, it has 4 modes. 2 of those modes decay with height, 2 of the modes grow with height. And in formulation and in the analysis, what we did? We only retained those decaying modes. So, what kind of disturbance are we talking about? That any disturbance that will decay with height. So, that cannot be a free stream turbulence effect, because free stream turbulence would be the other way, that it may not be able to penetrate inside the shear layer, but it is very much present outside. So, here that kind of a theory can only be verified by an experiment of the kind that was done by Schumacher and Kramstadt. They excited the flow from inside the boundary layer. You see the connection now? Unfortunately, eigenvalue theory would not tell you that. And what we basically then conclude, that the stability theory results are very relevant for wall excitation. And those modes which decay with height, we call them as the wall mode. You are now in a position to appreciate the fact that there would be cases where you would not be exciting the flow at the wall, instead you would be exciting the free stream, and if those modes are unstable or they can indirectly excite the wall mode, there has to be some coupling mechanism. You create a disturbance in the free stream, somehow it gets coupled and the wall modes gets excited, then you can generate these waves. Actually, Dietz in 1999 published a paper where he showed the same thing, that you vibrate a ribbon in the free stream at that frequency, at that fixed frequency, then you can see it gets coupled directly and you get again TS wave in the wall. So, there are ways and means. We will talk about how this coupling is performed. However, this is the paper that we wrote in 2002 showing how this coupling mechanism works. We looked at a problem of a different kind. We talked about a train of vortices going over a flat plate. You know, your free stream turbulence could be a sort of a combination of this unit process. The unit process we are talking about, I have a flat plate, I have vortices periodically passing over, convecting vortices. So, that is what we did study, and we then we realized that when we are looking at these vortices moving at a constant speed, it is rather interesting. Have you ever sort of paused and thought about all this thing, that we are talking about inputs which are steady, but all instability points at disturbances which are time varying. So, here also we are doing the same thing. We are talking about a train of convecting vortices moving at a constant speed at a fixed height. Despite that, you will see unsteady effects come up downstream in the over the plate. So, this actually was performed to find out what was the speed range at which this coupling is maximum. We did it because Jim Kendall of JPL did some experiments in a wind tunnel, and he did see a selective band of speed at which this coupling becomes very, very important. We will talk about that also, but let us now talk about how we set up the receptivity problem. We can do many things. We will start off with the simplest possible way of looking at the linearized Navier-Stokes equation and show how receptivity root for excitation applied at the wall creates GS. So, this is essentially this approach of doing problem is called a dynamical system approach, right. So, basically you have a fluid dynamical system, that is like your black box. You have some input, you are noticing some output. Your task in a dynamical system approach is to relate this input with the output, right. That is what we do. We will make use of some mathematical tool in terms of Fourier Laplace transform. So, be ready to understand that. And now we are talking about dynamical system approach. So, this is your fluid dynamical system. And this is basically being excited, let us say some simple thing, I call it x of t, and the output that I get, let me call that as y of t. Okay. So, there is something this box is doing, the black box is doing, that is what we call as the transfer function. I will call that as h of t. Well, h of t, and then it will be function of all the associated parameters of the problem, like what we showed for the cylinder. There Reynolds number is one of the parameter which was held fixed, but there was the other parameter, the various time scales, and the time scale means in that case it was the amplitude at Strouhal frequency was the thing. So, we can have all kinds of parameters here which we can call p, q, etc., and then we get this. What happens in Fourier Laplace transform theory or the Fourier transform theory itself, what we would show that the output is nothing but product of this transfer function in the omega space multiplied by the input spectrum. So, output spectrum is a convolution of the input spectrum and the transfer function of the system, right. Now, there are two ways of looking at this. You have done some experiments in your lab, etc., in dynamical systems or vibration analysis. What you do? You say you have done in a structural dynamics course, right? You vibrate the system at a fixed frequency. You have a shaker, and then you excite the structure with the shaker, and then you measure the response. That is what is called as the frequency response, because you are focusing upon a particular frequency, the frequency of the shaker. That is what we call as the frequency response. There is the other experiment that you have done even earlier in your school, when you did that experiment of swinging of a pendulum. What you did? You just gave it disturbance at t equal to 0 and let go the system. That is what we call as the impulse response of the system. You just give an impulse and let it go. Whereas, here in frequency response, you are continuously exciting the system at the same frequency. So, these two are different, but they are sort of complementary. The only interesting part is what you can say, the interesting major difference between impulse response and frequency response would be. Frequency response would actually latch on to the frequency of excitation. So, it is like a forced vibration problem, whereas impulse response, what it does? It allows the system a freedom to choose its so called natural frequency. So, that is why you should see that there is a merit in distinguishing between the two, although you can construct one from the other, but you be careful in interpreting your results. Okay. So, we will talk about this, but before we do that, let us talk about some groundwork that we require. Now, first talk about Fourier transform that you are familiar with. Fourier transform of a time varying function f of t is given by f of omega. How it is defined? Well, I just simply do e to the power minus I omega t times f of t and perform integral. What happens in this Fourier transform? Omega is real. Omega is always considered real. Please note that I have given the range of time from minus infinity to plus infinity. What does it mean actually? What does time t equal to 0 mean? When we are talking casually about instability theory, we do not even comprehend that. But when we are talking about dynamical system theory, then the time origin makes sense. This is where you begin the experiment, right. So, if I want to study a system, I switch on the system at some time, that would be my t equal to 0. So, that is why, although in notational convenience people do write from minus infinity to plus infinity, you would probably be writing about 0 to infinity. That would be a better thing to do. There is also associated issue of what we already know is the causality principle, right. I cannot expect to see some effect for something that has happened before even I started the experiment, right. It does not make sense. So, causality actually precludes that you consider this range of integral from minus infinity to 0. You would be well advised to start it from 0 to plus infinity. Now, if we have this quantity Fourier transform, this is called the direct transform as a function of different omega, I can synthesize my signal also like this. So, basically when you do frequency response, what you do is you try to get this f of omega, and if you do it over a large range of omega, and then you can construct the corresponding time varying function, which will have a mixture of all these frequencies acting together. So, that is one way of looking at it, right. Now, that is about time. Time is special, causality is special. When you look at space, then you do make use of what is called as a Laplace transform. Laplace transform basically is the counterpart of Fourier transform, but now the independent variable is space. And when you do about the space, well, we can do about what we just now talked about in the Fourier transform. I could just talk about a unilateral Laplace transform. Why it is unilateral? Because the range is from 0 to infinity. We are excluding minus infinity to 0 path. That is why it is a unilateral. We indicate it by subscript I. Okay. So, this is given by this. And what is important for us to realize that this path, earlier omega was real, but now we are talking about omega as complex, which has a real path and as an imaginary path. So, what happens is I can see that the real part constitutes the phase, isn't it? This is going to be your combination of sine and cos. So, this is the phase path, whereas this path actually directly conspires with the function to alter the amplitude itself, the magnitude itself, right. So, this is something what you need to do. Why do we need to make this alpha complex? Well, there are some nice elaborate theory, but we can understand it very clearly that existence of a Fourier transform is not always guaranteed. It is not always guaranteed. But suppose I take f of x, I can measure f of x, and then I can multiply by this factor which will attenuate that, then the integral may be convergent. So, if I take alpha I negative, then what will happen? That the original problem, if I just taken a real alpha r, may be difficult to perform this integral, but the moment I multiply it by e to the power alpha I x, then what happens? As x increases, those contributions are going to be damped, because alpha I is negative, right. So, this is how we can conceive of the requirement of making alpha complex, that we may or may not have the Fourier transform, but by resorting to Laplace transform we can improve its convergence property, so that it exists. So, this is what we need to do. Now, what we could do is, suppose in the alpha or alpha I plane, if I look at, what I could do is, I could take a line along which I will perform this integral. That is what I am doing. I am taking a line which is, say, alpha I distance from the real axis, and I am performing now integral from minus infinity to plus infinity. Okay. But along a line for which alpha I remains constant. So, this is this type of contours are called Bromwich contour. Okay. So, we take a particular contour to evaluate this integral, and we are talking about that as a Bromwich contour, and in this case the Bromwich contour has been chosen in such a way that alpha I remains constant. If alpha I remains constant, now what I can do? Now, I can perform the inverse transform, inverse Fourier transform on which function now? This multiplied by this, that is what I have written here. F of x e to the power alpha x is given in terms of this quantity. So, now you can see this is your direct transform, this is your inverse transform. That is for your unilateral Laplace transform. And what we did? We purposely chose a value of alpha I negative. Okay. So, what happens is, if I take alpha I further negative, then what happens? It will, if that particular alpha I, the integral is convergent, if I reduce alpha I further, it will be further more convergent, right. So, that is one thing that we can do. So, now what we can talk about, as I said, for space variation, we are not constrained by causality. So, I could actually take x going from minus infinity to plus infinity. That is what we are doing. When we do that, we call that as bilateral transform, and that is indicated by subscript II, okay, 2. So, f 2 of alpha, again I perform that integral going from minus infinity to plus infinity for all possible x. Okay. So, that is what we like to do. Now, if that is what we adopt, then we can write it in that as a sum of two quantities, right. This part, the range goes from 0 to infinity, and this part goes from minus infinity to plus infinity. So, if I take f of x, which could take all possible values, this is nothing but f of x times u of x. What is u of x? It is a Heaviside function, right. What is Heaviside function? Well, let me do it like this. Say u of x minus x naught. So, what I do is I mark up a place x naught, and this has the property that this is 0 all the way up to x naught, then it goes there and remains constant. This value is 1. Also it is called unit step function, Heaviside function or the unit step function. So, it takes a unit value and goes like a step. So, that is what it is. So, my original function can take anything, but because of this I am only performing integration from 0 to infinity. It is almost like multiplying that f of x into u of x, and this one I can simply think of f of x multiplying u of minus x, because that is what it would be. It would be for all negative x, it will be 1, for any positive x this will become 0. right. So, that is the complementary thing. So, what happens is, as I told you, that if I do this transform and I get that alpha I x there, if that alpha I x for a particular alpha I x it has worked, what will happen? It will work for any other alpha I x. Remember, this was negative. So, now it can go up. So, that is what it is. So, this first integral would be given by this shaded area like this, which is above this line. So, this line, if I call that alpha I is equal to gamma 1, so that is the lower limit. The same way, the second part would be defined in a region which will be below another line, and this line I will call it as alpha I is equal to say gamma 2. That means what? A part of the integral is valid in this region, another part is valid in this region. So, the total together will be valid in this cross hatched area. So, this is the way how you construct the Bromwich contour. We said that it has to be taken from minus infinity to plus infinity, but you do not have the liberty to take it everywhere. So, by this logic you can say that this is the region where your Bromwich contour can lie. Well, this is something that we keep in the back of our mind, that we need to, given a problem, we need to identify a Bromwich contour along a strip of convergence. So, this is the strip of convergence. Now you can see we have worked it out. A part is valid in this part, another part is valid in this. So, this is the common region where both the parts are valid. So, that is your strip of convergence, that is spanned by, let us say, gamma 1 and gamma 2. And so, when we say choose this wave number, complex wave number alpha or alpha I, we need to take it somewhere. There is no need for you to take it along a constant alpha I line. It is only that you should be in the strip of convergence. You can do it anything that you wish, but you would notice that we do rather very efficiently when it comes to fast Fourier transform. And what do you do in a fast Fourier transform? You go along the real axis omega r, right. So, here also we can adopt the same picture. I can just shift this thing to this. That is what we have done here. Whatever the fx was, we just shifted it by e to the power alpha x, and then we performed integral for alpha r ranging from minus infinity to plus infinity. So, I could perform this part very easily using my FFT routines, and this is what we would be doing, because we would like to use FFT. It is just a matter of importance for us to remember that what we get out of fast Fourier transform is much more accurate than if we would have performed some kind of a numerical approximation. This I jokingly call slow Fourier transform. Okay? If you compare your standard Fourier transform with fast Fourier transform, it is actually the fast Fourier transform is more accurate. So, do not think of some problem, I will spend more time, I will write out a program and I will evaluate it slowly. That will be not only slow, that will be inaccurate also. Okay? So, we should remember this. So, now we know what is a Bromwich contour. I suppose from this point on you should not be very much surprised. Unfortunately, though, not many people use this Bromwich contour integral method. So, what you are seeing here is what we are going to perform. So, I have underlined that Bromwich contour lies inside that strip of convergence, okay? And that strip is defined by alpha I ranging between gamma 1 and gamma 2, right. Okay. This is what we have worked it out on the blackboard. So, you have no problem in understanding what we just now talked about. Now, let us talk about the interpretation of Bromwich contour. What does it mean? You see, we found out that one part of the integral is valid for x positive, another part of the integral is valid for. However, what we are doing, if we are inside the strip of convergence and we perform that integral along this, let us say, fixed alpha I contour here, then what happens? I am going to get information for both what is happening downstream as well as what is happening upstream. Right now, this quantity that we are talking about f 2 of alpha, it is something like our in the Orr-Sommerfeld equation that phi. You recall that Orr-Sommerfeld equation is an equation for the Laplace transform of stream function or the normal velocity that we have established. That phi, that equation that we write, is basically what? Disturbance quantity. So, let us say that is like my psi this thing, and what I do, what we did, we wrote it like, well, there will be factors, So, let us say we make a point of view is that we write it like phi, that is what we did, and phi was function of y, of course, height from the wall. It was also function of alpha, and if we excited the system at a fixed frequency, then that would be that, and then we did it like this, e to the power I alpha x d alpha. So, now you can see the connection. This quantity is the Fourier Laplace transform of the disturbance psi, and the governing equation we have worked it out. So, the governing equation, how did we work it out? Let us say ODE, we will solve it, but when we apply the boundary condition, how did it appear? If you recall, we only looked at the wall mode, right. When we looked at the wall mode, we removed two modes which actually grow with y, we only retain those ones which. Then we fix those multiplicative constant by satisfying the boundary condition at the wall, and in the process the expression of phi came out to be something like a numerator by denominator, right. We will do that shortly, and you will see what I am saying, but let me just verbalize what we are going to see. So, this phi itself, when it is the solution of the differential equation and it has satisfied the boundary condition, it takes a form numerator by denominator. Now, what happens? Your exposure to complex analysis, if you recall that you would have situation where the denominator is 0, and those points are called what? The poles, right. So, now you can see all that we have learned has not gone unused. Now, we are seeing the merit of learning all those, and there also we did all those integrals going from minus infinity to plus infinity, indefinite integrals. That is what we are going to do, and this is very familiar to you. You recall that we used to do some integral, if we have to do it from minus infinity to plus infinity, we take a semicircular arc, and then everything was taken care of. Okay. So, now what we just now said, this f has a role like what we talked about, the amplitude of the disturbance stream function or the normal velocity, and then we said it will be of numerator by denominator form, and the zeros of the denominator provides you with the poles, and those poles are what? Your eigenvalues, right. So, basically what does the transfer function now tell us? Transfer function is something like your amplifier, right. So, if you give a very imperceptible small disturbance, and that disturbance happens to be the pole of the transfer function, then you are dividing by 0. So, you are basically amplifying it. That is this connection between your receptivity and eigenvalue analysis. Now, you can see that what we assume that we are dividing by 0 means we are trying to excite the system at those eigenvalues, and if I have also numerator it is not exactly equal to 0, or even if it is vanishingly small, then we have indeterminate form 0 by 0. So, despite the fact that input is virtually absent, because of this indeterminate form we still get a finite limit, and that is your eigenvalue, eigenfunctions, right. Now, you can see the connection, but however, those values that we will obtain, as we have seen, could be a point like this, which will have a value of alpha r and a value of alpha I. Now, we have talked about group velocity, right. So, what is the utility of that group velocity? That comes to your rescue here. You have identified the eigenvalue, but how do you know whether this eigenvalue corresponds to a disturbance that is going downstream or upstream? You will have to find out the associated energy is going in which direction, and that direction of the energy propagation is given by the group velocity. So, let us say this point, that P1 that we have found out, that is a pole, has a positive group velocity. So, what does it mean? This disturbance will go downstream, positive group velocity. If it was negative, then it would be like this. So, what happens is, you must be already started thinking that a priori when I start a problem, how do I fix my Bromwich contour? So, we are giving you the recipe step by step, that you identify all the eigenvalues, calculate their group velocities, and then you see which is going in which direction. So, each of the eigenvalues have to be associated with upstream propagation or downstream propagation. So, in this case P1 corresponds to, let us say, the downstream propagation. Then what happens is, I am performing the Bromwich contour integral from minus infinity to plus infinity like this. Now, what do? I can close it like this, and because this is a pole, I will have to isolate it. I dent the contour, indent the contour and go around. Then what happens? Inside the shaded area, your function is analytic, right. Then you can use all of those nice properties of Cauchy's theorem, Cauchy's integral formula to help you in finding out the response. However, you realize also in all such activities that you have done in a complex analysis course, you have assumed that the contribution of the integral along the semicircular arc is 0. That is what is called as the Jordan's lemma, right. Now, you see Jordan's lemma actually gives us a very vital guideline. How do we use the Jordan's lemma, which says that the integral along this is going to be 0. So, what happens if I perform this integral, and this is a closed integral, the function inside is analytic. So, what happens to the integral by Cauchy's theorem? 0, right. So, it is 0. So, what happens is this integral plus this integral equal to 0, but then what have we done? We have to also include the contribution coming from there. So, that contribution goes to the right hand side. So, what happens is then integral along this Bromwich contour in the presence of Jordan's lemma is equivalent to your 2 pi I times sum of the residues. That is your Cauchy's theorem, right. So, that is how we go about it. It is all very nice and clear, but the only thing is you will have to make sure that Jordan's lemma is good enough here, and there are some ways of finding it out whether the Jordan's lemma is good or not. We can figure it out, but if Jordan's lemma is good, then if we perform the integral directly along the Bromwich contour, then we are going to get the solution for both upstream propagation as well as downstream propagation. You see, somehow if you look at all the textbooks on instability theory and the associated mathematical formulation, they just simply have no clue. They just simply say up to some distance there is nothing, all of a sudden some disturbance comes and it goes in the downstream direction and so on and so forth for a fluid flow. Now, if that happens, then we are talking about some kind of a discontinuous behavior at the excitation, but we are talking about incompressible flow. How can you reconcile to that fact that you have a very analytic functions, the solutions are supposed to be possessing all kinds of derivatives and continuous, and at the same time at the excitation you have a jump discontinuity. This cannot be necessarily true. So, what happens is this Bromwich contour integral solves that issue, because it gives you a solution both upstream as well as downstream. And what is more important also, you realize that instability theory, what we did find out, we did look at the solution contribution coming from individual eigenvalues one at a time, right, and then that is what we call as the normal mode analysis. So, each of the individual eigenvalues are one of the modes, and we sum it over, that is what we do, right, 2 pi I times sum of the residues. So, each one of them working independently. But we have also talked about the group velocity. What did we see? That waves interact and it can form groups, but this normal mode analysis does not seem to give you a direct connection to that. So, we have to be careful in interpreting our result. Furthermore, we would also have to ensure that the solution of Orson-Field equation as obtained satisfies Jordan's lemma. Okay. Now, this is one issue. We have also made one assumption here, as you can see here, that we have performed the integral, over alpha. What did we assume? That here the system is excited at a fixed frequency omega naught. It is an assumption. If I excite a system at a frequency omega naught, for a stable system, I can think of that response also will be at omega naught. But whatever we are doing it for alpha, allowing the system to pick out its natural frequency, that can happen also with the time variation. So, what is the guarantee that if my input is at frequency omega naught, output also will be at omega naught? This is more like an assumption. Whenever we do that, we call that as the signal problem. So, if I excite the system at a frequency omega naught, output is also at omega naught. This is what we call as the signal problem. So, please do understand that this is an assumption which we need to really check it out. Well, you can very clearly see how to check it out, that you do not need to make that assumption. You can also perform the integral over omega. Whatever you are doing in alpha plane, you can also do it in the omega plane. And now, omega also is going to be complex. Omega also is going to be complex, and you will have to be doing this Bromwich contour integral in the alpha plane, in the omega plane, right? And then you would get a composite solution. We will talk about some of those exercises. However, before we do that, we need to understand that what we have achieved so far, that we are studying linearized Navier-Stokes equation. By now, all of you with me that Orson-Field equation is nothing but the spectral representation of linearized Navier-Stokes equation. I have just written it in the alpha plane, right? That is what we have done. So, we need to really do some of the studies that we need to be aware of. Now, let me talk about some simple Fourier Laplace transforms which are rather useful however, I think before I do that, I should tell you some little bit about the properties of Fourier Laplace transform, because you may not all have done it before. So, basically we will talk about some properties. So, it is basically a short tutorial on Fourier Laplace transform. So, let me go through it simply with you. Then say if I talk about a function f of t, I said from the this is the inverse transform, right. So, we what we do is we take this direct transform f of omega and perform this integral I omega t d omega. Okay. Now, at any point of discontinuity wherever we may have, as we have seen, like a unit step function is a discontinuity. What we do at the point of discontinuity, that would be written as the average of the right hand limit and the left hand limit of the point of discontinuity. Okay. So, that is the usual way that we should be talking about. Now, f itself could be, let us say, f 1 plus I f 2. Okay. Now, what I could also do is I could also represent this f of omega as a real part plus an imaginary part, right. This is what we should have. So, what one can show rather clearly that r of omega, the real part of the Fourier transform, can be obtained from this f 1 cos omega t plus f 2 sin omega t. I have just simply opened up the integral and then we perform this integral, that is r of omega. And the imaginary part will be minus of this, that will be f 1 sin omega t minus f 2 cos omega t. So, we can obtain the Fourier transform. See, basically you can understand that we are not talking about physical system. So, f of t is kept in its general form, it has a real and imaginary part. For a real function, of course, you will not have that luxury. What happens is, if f of t is real, then we can very clearly see that f 2 is 0. So, r of omega would be nothing but f 1 t cos omega t dt. And this integral is of course from minus infinity to plus infinity, right. Cosine function is what? Is a even function or odd function? It is a even function. So, what I could do is I could just simply write it as 2 times 0 to infinity f 1 t cos omega t. So, whenever you can write it like this, you call this as a cosine transform. The same way one can obtain the value of I of omega. What happens to I of omega? Of course, this part is gone and this is an odd function and I am performing integral from minus infinity to plus infinity. So, the negative part will cancel the positive part, this will identically equal to 0, right. So, we can make use of that property. Now, this is of course true when we have said this f1 t is real and even, right. We have to be careful. If f of t itself is real and odd, then all this logic flips over. Then r of omega will be 0 and I of omega will be 2 times that split integral, right. So, please do understand some of these subtle issues. Now, let us enunciate some of the properties of Fourier transform. One of the property is of course the property of linearity. What does linearity property imply? That if I have a function f1 t whose Fourier transform, let us call that as capital F1 of omega, and similarly if I have another function f of 2 whose Fourier transform, let us say, is given by f2 of omega, then linearity simply says that f1 plus f2 is the Fourier transform of f1 plus capital F2. So, this is the linearity property. Please do understand that it is not necessary that your actual unknown have to be equal to a linear function. It could be nonlinear, but this transform is a linear thing. So, it can be applied to irrespective of whether the function is linear or nonlinear, it does work out the same way. There are some other properties which are quite often used. For example, one often uses the symmetry property. The symmetry property says that if I have a function f of t related to its Fourier transform f of omega, then I could show very easily this f of t is a Fourier transform of 2 pi times f of minus omega. I am just enunciating, you can actually plug it in the basic definition and can show it. So, that is your symmetry property. There is something called the time scaling property. The time scaling property comes like this, that if I have a real function constant, let us say alpha, then I have, let us say, f of t given, I scale that time by this function alpha. Its Fourier transform would be given by this. So, there this time scaling property actually is a very interesting thing. What it says, that if you have a function which is stretched in the time plane, in the frequency plane it is squeezed, right. So, that is what is what we already know from the properties of Fourier transform. If I have, say, a periodic function going from minus infinity to plus infinity in the time plane, the corresponding Fourier transform is just a single point, it's a delta function, right. So, same thing happens, it is the other way around. If I create an impulse, I create a disturbance at t equal to 0, it excites all frequencies. Now, you know that what was we were talking about earlier about the frequency response vis-a-vis the impulse response. Why impulse response is so much more preferable? In performing the impulse response, I am actually exciting all frequencies and the system can latch on to its natural frequency. But in performing an experiment with frequency response in point of view, I have to really go scan, and I should not have to. I will have to worry about if I am missing exactly the peak or not. So, you see, impulse response is a much better thing to do. I think we will stop.